Hello everyone, my name is Jinhong Wang from Imperial College London. I'm going to introduce a passively compliant idler mechanism for underactuated dexterous grippers with dynamic tendon routing in this presentation. In this presentation, firstly, the research background of the literature review will be introduced, which can then lead to the aim of the project. After that, the novel idler system and its implementation on a reconfigurable POM will be explained. Finally, the performance of the system and the results will be shown and discussed. The dexterous in-hand manipulation capability of grippers has drawn lots of research attention due to its importance in enhancing the adaptability of the robotic systems, and the optimized actuation method of the robotic finger is still an open research question. The tendon actuation method has been one of the most common ways to control self-adaptive underactuated fingers. Ideally, separate actuations of each finger is favored for dexterous manipulation, but it will inevitably increase the cost and building complexity. As an alternative, actuating all fingers with single motor provides a simpler and cheaper solution. Here on the slide are two prosthetic hands with individual motors controlling each finger, as you can see on the slide. The separated actuation provides high dexterity in manipulation. However, it will be more expensive and complex to control due to these increased number of actuators. In contrast, using single actuator to control all fingers can provide a cheaper method. Two concepts are shown on this slide: a closed-loop tendon mechanism and a cascade of floating pulley systems. In both concepts, grasping forces are differentiated by the mechanical design rather than the separated motors, and simplify the actuation by a lot. However, in order to perform more dexterous in-hand manipulations, it will require the change of the finger positions, which means the difference in the tendon length, and these hands are not capable of doing that. Therefore, our aim of the work is to provide a solution that can allow gripper with single-input, multi-output tendon systems to perform dexterous manipulation, and the unsynchronization of the tendon caused by the manipulation can be avoided. Therefore, we came up with a novel idler system to achieve this aim. Idlers, or tensioners, were usually used in flexible mechanical transmissions such as belts or chain drive systems. Their main purpose is to increase the wrap angle on the driving pulley or the sprocket so that the force transfer capability can be maximized. To ensure the performance of the transmission, the belts or the chains must be kept in the tension during operation, and the same concept applies to the design of the tendon routing systems. When a tendon is routed, the total length is fixed. For robotic hands with reconfigurable palms, it is common for finger positions to change relative to the actuators, which means the fixed tendon length will either become too long or too short for the same finger posture. Hence, the fingers might lose contact with the grasped object. However, with the idler system illustrated in the figure, the access length can be actuated or eliminated by the vertical movement of the idlers. In addition, the grasping forces were also provided by the spring until the idlers has reached the topmost position. A few criterions listed on the slide should be satisfied to ensure the grasping forces. In order to show the performance of the idler system, it is implemented on the reconfigurable palm based on a 5-bar linkage with 3 underactuated fingers located at its moving joints. Therefore, when reconfiguring the 5-bar linkage, which is the gripper's palm, the fingers will move relative to the base where the tendon actuator is mounted. The length of the tendons will hence need to be adjusted in order to maintain the grasping forces. In addition, the tendon length change of each finger is different from each other, which provides more problems of the actuation. The idler system were hence incorporated with the gripper to make tendon actuation possible with only single motor. As shown on the figure, the idler supports were integrated with the bases to increase the strength of the support. The full heights of the base were utilized to maximize the potential tendon actuation length. Dowel pins and pulleys were utilized to reduce the friction, and the tendons were routed near the top plate without hindering the adjacent idlers and spring. This figure shows different configurations of grippers with corresponding idler positions. Parallel, T-shaped, trigonal grasping configurations, and it is clear that the position of the finger bases moves a lot. Since the total length of the tendon is fixed after routing, when the distance increases, the idler will be pulled up and the grasping forces will increase correspondingly, and vice versa. Here is a direct comparison between the two grippers, one with the idler systems and the other one with tendons directly fixed to the actuator. The tendon actuation will held still and the palm was reconfigured during the video. It's clear that during manipulation, the gripper with the idlers could keep the grasping forces and maintain them at a sufficient level. In contrast, the other gripper failed to perform a grasping posture and a large fluctuation in the finger positions. This slide includes a close view of the gripper base showing the idler system during manipulation. As you can see, tendons were all kept in tension and all the finger posture will remain the same. Although there will be fluctuations in the grasping forces due to change of the idler positions, it can still keep the grasping forces at sufficient level and it will be relatively small compared to the change in the gripper without the idler system. As for the manipulation test, three force sensors were fixed to the central support block as shown on the top figure. A silicon case was then made to provide the housing for the sensors and also make the test objects easier to grasp. In addition, testing objects with a variety of sizes were employed to prove that the gripper is capable of for in-hand manipulation. 3 repetitions were carried out for each set, and one of them will be shown in the following slides. This slide shows the comparison between two grippers. Both the translational and rotational trajectories were performed. From the data of both of the trajectories, it is obvious that the gripper with the idler system is able to maintain a higher average of the grasping forces during manipulation than the gripper with the tendons that are directly connected to the actuator. In addition, during the experiments for the comparison group, we found out that without the idler system, the gripper is impossible to grasp the object with different grasping configurations, let alone to perform an in-hand manipulation. Apart from the force testing, the grasping and the manipulation capability is also examined by objects with different sizes. Two modes of manipulation were shown, and it is clear that the idler system is able to maintain the grasping forces at a sufficient level, and thus guarantee the manipulation. To sum up, the introduced idler system is capable of maintaining the grasping forces. Although a few of the readings dropped close to zero, it was due to a change of the contact points on the fingertip during manipulation. In addition, the experiments shown that the larger tendon length difference will lead to a large fluctuation in the contact forces readings. This is expected based on Hooke's law. The average grasping forces, however, is largely dependent on the neutral position of the tendon routing. Therefore, unlike those grippers in the literature review, the grasping forces of different fingers implemented with idler systems can be adjusted individually by changing the initial length of the tendons routed on or the spring in the idler system. As for the further improvements, we found out that sometimes the bending of the 3D printed materials could undermine the performance of the gripper. In addition, large friction were caused between the tendons and the structure, hence a better tendon routing method could be applied to improve the performance. That is the end of my presentation. Thank you very much.